Hello students. In today's video, we had to start with arithmetic logic unit. What is arithmetic logic unit? It's a unit present in 8085 microprocessor, which is of 8 bit, which is used to perform arithmetic and logical operations. And depending on the arithmetic and logical operations answer, the flag register is either set or reset. Set means 1, reset means 0. So let's see what's written in here. It is an 8-bit unit where arithmetic and logical operations are carried out. Okay, arithmetic logic unit is a digital circuit present in 8085 microprocessor. The ALU consists of binary adder. Binary adder, if you remember when we had done the block diagram of generic microprocessor, there ALU is the diagram of ALU is shown in detail. Let me show it to you. It's here. Can you see this ALU? Here, if you can see, it has flag register. Can you see this adder? The binary adder which I was talking about in ALU, arithmetic logical unit of 8085, it was talking about this binary adder. It is also a block present circuit within the circuit. ALU is a digital circuit. Within that, it has a circuit named binary adder. Okay, and with which accumulator is connected and temporary register is connected. We had learned about accumulator and temporary register in previous video. So let's get back to where we had left in ALU of 8085. Here it is. It is an 8-bit unit. This we had done finish reading. Here we were here. The ALU consists of binary adder. The adder is mostly for binary addition and subtraction. Binary adder circuit we had discussed in 11th also. This binary adder is in depth in CS2 syllabus of 11th standard. This adder is used to perform binary addition. So this binary adder, it performs only binary addition and subtraction by the 2's complement addition method. If you remember in CS1 first chapter, number systems, we had done subtraction by 2's complement method. So this binary adder performs binary addition and also it performs subtraction by 2's complement method. Okay. Accumulator, input output device and memory act etc. supplies data. If you remember when we had done accumulator, so the purpose of accumulator is, one of the function of accumulator is it holds the operand. What is operand? When I'm doing 2 plus 3, then 2 and 3 are operands. So one of the operand is stored in the accumulator, if you remember. So yes, accumulator can provide supplies data to the microprocessor because one of the operand is stored in accumulator. If I want to perform addition 2 plus 3, 2 is stored in accumulator, B is stored in 3 is stored in B register. If you remember, we had discussed this instruction, add instruction. So accumulator supplies data to the microprocessor, or any input output device which is connected to the microprocessor can supply data. Memory, main memory can provide any type of memory. After performing the operation, it sets the flags according to the nature of resulting answer. As I had told you, ALU is after performing arithmetic and logical operations, it either sets or resets the flag. Set means 1, reset means 0. Okay, so according to the nature of the resulting answer, it either sets the flag or resets the flag. Now, if my answer is 0, Z flag will be 1. When my answer is non-zero, when my answer is 0, Z flag is 1. When my answer is not 0, Z flag is 1. Okay. Detailed explanation of flags we will be discussing in the next topic. Here, as you can see, this is ALU. ALU is connected to flag because after performing arithmetic and logical operations, it sets flag or resets flag. Temporary register, if you remember, is used to store one of the operands. Also, accumulator is also used to store one of the operand. The another function of accumulator, if you remember, accumulator is used to store the result after performing a plus b, for example, or 2 plus 3, the answer is 5. Answer will be stored in accumulator in itself. If you remember, in previous video I had explained the add instruction. Okay, so one of the function of accumulator is one of the operand is stored in the accumulator. The second function of accumulator is that after performing the arithmetic and logical operation, result is stored in the accumulator. And this is of course data bus. Okay, and the control bus, if you remember, address bus, if you remember. Now next topic is flags. Flags, what is actually flag? Flag is a register, special purpose register, which is of 8 bit in 8085 microprocessor. Though flags is of 8 bit, but only 5 bits are useful in flag register, and the remaining 3 are unused. Flag register is used when after performing arithmetic and logical operations, when ALU performs arithmetic and logical operations, according to the result, it either sets the flag or resets the flag. So there are total 5 flags in 8085. Okay. So let us discuss this in detail. These are single bit status registers. Single bit means Z flag when I am talking about. So Z flag can be either 0 or 1. So it is 1 bit, either 0 or 1. So the status register, these are single bit status registers, or you can say flip-flops. Flip-flops is a circuit that has 2 states and can be used to store state information, either 0 or 1, operated by ALU. I hope by now you have understood this sentence. The flags are either set or reset. Set means 1, reset is 0, according to the answer produced by ALU. It is important because flags are examined in conditional instructions. So why flags are important? It is important because it is used when I am using conditional instructions. What are conditional instructions? For example, after performing the some instruction like add, and the carry is there. Carry is one of the flag out of those 5 flags present in 8085. So carry flag is when carry is present. Carry means when you are adding two numbers. For example, I will show you the example. 1 0 1 1 0 0 0 1. Okay, this is one of the operand. Here 1 0 0 0 0 0 1 0. So if you remember the binary addition which we had done in 11th standard, first chapter of CS1, the addition of binary numbers is 1 plus 0 is 1, 0 plus 1 is 1, 0 0 is 0, 0 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 0 is 0, and 1 plus 1 is 0, carry 1. So if the result is carry, okay, so when my answer carry is present, so the condition is when carry is present, jump to this particular location. This can be a conditional. These such type of instructions are known as conditional instruction. In this case, flag is used like jump. Here it's I believe jump is unconditional instructions. These instructions we will learn in chapter 2. So you don't have to worry that from where we'll come to know which instruction is what. Of course, all the 74 instructions are explained in detail in chapter 2. So jump is actually, it is written wrong. Here jump is unconditional instruction, not conditional instruction. But call is conditional. Okay, so we will learn about this in detail later. I hope you are clear with conditional instructions. Okay. Okay, one more thing I want to tell you is these are how many bits? 1, 2, 3, 4, 5, 6, 7, 8. 8 bit. Okay. If you remember our registers, accumulator is of 8 bit. B register is of 8 bit. So if this number is stored in accumulator and this number is stored in B register, so A plus B and the result is this. I hope it's clear why I have taken 8-bit number over here. So as I told you, the flags are total 5. There are 5 flags. The name of the 5 flags are sign flag, zero flag, auxiliary carry flag, parity flag, carry flag. So let us study each one in detail one by one. So the flag register, if you remember, is of 8 bits. 8 bits out of which only 5 are useful and the remaining 3 are unused. So this is flag register. These are the contents of flag register. This 0th bit is carry. First bit is unused. Second bit is parity. Third bit is unused. Fourth bit is auxiliary carry. Fifth bit is unused. Z flag is sixth bit and seventh flag is sign flag. Okay. So this is the sequence you have to learn. You cannot shuffle the position of any flag. For example, you cannot write carry on second position and parity on 0th position. The position of the flags is fixed. You should remember this. Now, for example, here we'll do this later. First, let me explain each one of the flags. Z flag. What is the use of Z flag? Let's see. When answer is 0, Z flag is 1. Answer is not 0, Z flag is 0. 0 means reset, 1 means set. When carry is not present, carry is 0. When carry is present, carry is 1. Parity odd. Parity is odd means the number of ones present within the number is odd. That time P is equal to 0. When number of ones within the accumulator is even, if we'll count the number of ones within the accumulator, then the parity is even. For example, let us check here this example. For example, this is the content stored within the accumulator. So 1, 2, 3, 4. Parity is even. Let us check this 1, 2, 3, 4. Okay, here it is even parity. Likewise, if in the accumulator, if the answer has if the answer has the odd number of ones, then the parity is odd. Then next is plus and minus sign flag. It is for sign flag. When answer is positive, the D7th bit, when this bit is 1, when this bit is 1, answer is positive. When this bit is 0, D7th bit is 0, answer is negative. That is what it meant. Mostly sign flag is used when we are performing subtraction, not in addition. There is no need for sign flag in addition. That time we ignore the 7th bit. That time we ignore, but during the subtraction operation we check, the processor checks the G7th bit. Now why parity is used? We know about zero flag, we know about carry flag, we know about sign. What about parity? Parity was used before in older processors to check the integrity of the data. Integrity means what? Whether when I'm performing 2 plus 3 and I'm getting 4, is it right? No, the answer is wrong. Due to some failure, due to some error, my answer is not correct. So it was used to check whether the answer is correct. It was used for checking the integrity of the data. So now it is not used. Now these were used in previous processors. Let's see what's written next. With instruction STC carry flag. STC is one of the instructions out of those 74 instructions which we are going to learn in chapter 2. STC flag means set carry. It directly sets the carry flag. Okay. Table 1.3 illustrates different conditions that we have discussed. Table 1.3, conditions of ALU result and the status of flags affected. So one thing I want to clear, that this parity flag we don't have to do much in detail, but you have to keep in mind that it was used for checksum, for checking the errors, to check the integrity of the data, and it was used in older processors. Now it is not used. We are not supposed to do this in detail because it's not there in your syllabus much in detail. So here we were here. After execution of arithmetic operation, execution of arithmetic operations, program status word is formed. What it is? PSW, program status word. It contains accumulator with flag. So contents of accumulator and contents of flag is stored in PSW. When the combination of accumulator and flag register is known as PSW. When accumulator is used with flag register, then PSW is formed. What is One thing I want to explain is, just see this. These are the bits. For example, here sign flag is 1, Z flag is for example 0. If nothing is there, it is not used, it is of course 0. Auxiliary carry is 0. For example, this is unused, so here also it's 0. Parity is 1, 0 because it is unused. Carry flag is 1. So this is binary number. If you remember, this is 8-bit 1, 2, 3, 4, 5, 6, 7, 8. Now this is binary number. I want to convert it into hexadecimal. So how we convert a binary number into hexa? For example, this is the number 1 0 0 0 1 0 1. This is the number 1 0 1 0 0 0 0 1 0 1. Now what we will do? We will represent each digit in hexadecimal represents 4 bits. I've already explained this. 4 bits. That means 8, 4, 2, 1. Similarly, 8, 4, 2, 1. So wherever there is 1, we will add this. 4 plus 1 is 5, 8. So 85H. So what is there in the flag register? Flag register is equal to 85H. Okay. This is how we calculate the value of flag register. There can be different values, like here it can be 0, it can be 1, this has to be 0, it can be 1, 0, 0, 0, 1. So this is how we can convert the binary number into hexadecimal, and we will come to know that flag register, will come to know the value of the flag register. So what it is saying, or for example, now you see accumulator has some value, for example 15H. Okay, it's a hexadecimal. In 8085 the data is stored in hexadecimal, and for example flag register is equal to 85H. 85H. So the combination of accumulator and flag register forms PSW, program status word. So PSW is equal to, if you remember, I have already discussed lower address byte and upper address byte. So if you see, accumulator is higher order byte and flag register is lower order byte in PSW. Okay. So this we don't have to learn much in detail. Just keep these things in mind which I have told you about PSW. Okay. Then after the execution of arithmetic operation, program status word is formed. Why it is formed? Because after performing the arithmetic operation, result is stored in accumulator and flag registers are affected according to the answer. So accumulator along with flag register forms PSW. Next topic is program counter. Program counter I had already explained in one of the videos, program counter and stack pointer. So there is no point for me to explain you this here. Just I want to tell you I'll just recap. Program counter is the 16-bit register which is used to store the address of next instruction to be executed. And I want you to make few of the corrections here, like here in 0004 it should have, I want you to assume, sorry, whatever is written over here, just you have to assume, just assume that here 0 0 0 9 is here. Okay, and also assume, just do the corrections in the textbook, then only it will be clear to you. There are minor mistakes which might confuse you. For example, here already one of the data is stored 00 00 H represents hexadecimal, and here just assume that any data, not let it be 33 or make it 51H. Next, just assume that here also 00 is stored, 00H, and here also 80H. These data are already stored in the stack memory. And here 00 00 and 33 is stored. It's already given in the textbook, 00 and 33. Okay, and here let it be 0004. This is not correct. 0004. So when you will read the paragraph on stack pointer from the textbook, it will be easy for you to understand. Just watch the video which I have created on program counter and stack pointer, and then when you will read this, it will be easy for you to understand. Okay, stack pointer is also 16-bit register, and the rest of the details you can check from the video, and do make sure you do these corrections. Here also you have to make few changes, and one more thing I want to explain here is stack is a memory. Okay, it's not a register. Stack is a memory and stack pointer is a register, 16-bit register. Why 16-bit? Because this is hexadecimal number, and in hexadecimal each digit represents 4-bit. So 4 plus 4 8, 4 12, 12 plus 4 16. So stack pointer is of 16-bit. Stack is a memory. There are two types of memory, stack and queue. This I have explained you in my video on stack point program counter and stack pointer. In stack is based on LIFO. LIFO is last in first out, and queue is based on FIFO, first in first out. Okay, so stack is a memory and stack pointer is the 16-bit register. Okay, don't get confused with the term stack and stack pointer. And also here few of the corrections are required. The corrections are, here you should write 0007. You have to make it 0007 instead of 0003. Make it 0007, and instead of 0004 you have to write 0053. You have to make it 0005. Okay, this is lower order byte and this is higher order byte. So these are the corrections you have to, these are the changes you have to make in the textbook so that it doesn't confuse you, because there are minute mistakes in the textbook. So for today we will stop here. In next video we will discuss incrementer decrementer register, and then we will discuss instruction decoder. Thank you.